Part 5 Stability Verification Test SVT. Several procedures proposed to verify the stability predictions of the compressors, similar to type 1 or forced excitation during the mechanical run test. The stability verification test provides confidence in the analytical prediction regarding the stable level and location relative to the stability ratio to show the robustness and optimization of machinery design. This test required additional temporary hardware, mounting bearing exciter. See to the next page. SVT takes the constant time, however. SVT is technically effective alternative means compared with the highly expensive Type 1 test. SVT is carried out to measure the real stability margin of the compressor, identifying the system mode and their log decrement. Usually for compressor, fast-forward mode has dominant influence on stability during operation caused by fluid dynamic effect. To evaluate the rotor stability, active magnetic bearings to be used for excitation of rotor during operation. A and B shall be mounted on shaft end of compressor for easily removable after test. So figure 5.2 and 5.3 you can see. This figure shows the mounted magnetic bearing exciter on the shaft end. This is the thrustics. The shaft end is expanded to install this exciter of the magnetic bearing on the shaft end. And this figure shows the cross-sectional drawing of the compressors. This is the shaft and the bearings, radial bearings, and the impellers are located. And this is the balance piston area, and this is the inlet, and this is discharge. And this is a coupling, and the power is transmitted through the couplings. On the shaft end and the end, the magnetic bearing is installed as exciter. This is the schematics of the rotor system of the existing exciting test. The rotor supported by bearings and shaft end exciter is installed, and during rotation, all bearing has a spring and damping, and each seals has some of the effect on excitation. And during rotation, this magnetic bearing, through the magnetic bearing, the force is excited on the shaft and to check the rotor stability during the test. This is a schematic drawing of the rotor excitation system. So this is installed magnetic bearing and AMB controller system are connected, and using these tools, so we can excite the rotor from the externally. Log decrement shall be measured at two different operational conditions, baseline and full speed, full density, in order to plot the measured real applied cross-coupled stiffness versus log decrement, and to extrapolate the curve to the minimum log decrement at worst design condition. Applied excitation method used for stability test is shown in this table. The log decrement shall be measured at two operational conditions as follows. A. Base stability. Log decrement at base stability is measured during mechanical running tests with near zero internal cross coupling and low pressure condition, or high speed balancing test. B. Full speed, full density test. Log decrement at FSFD condition is measured in condition that the pressure, temperature, flow rate, and bearing temperature is stabilized, which shall be equal to the site operating condition with specific cross coupling. Typical full speed, full density test condition is shown in this table. This is specified operating condition on site, and this is intended test condition at shop. So Specified gas is hydrocarbon, and the molecular weight is near 22, and test condition is inert gas with combined with argon and helium, and molecular weight mixed molecular weight is 25.57. That is a little bit higher molecular weight than the spec conditions. And speed is a little bit higher, and also the discharge temperature is too much higher than spec conditions. And power is almost same, and the inlet pressure and discharge pressure is almost same. Typical test results are shown in this figure. The stability comparison between the labyrinth with and without shunt hole. So this is the rotational speed versus log decrement. Baseline stability test is a low pressure operation based at the pressure of the zero point 0.2 MPa and without shunt hole. And when we increase the pressure, uh, is 4 MPa conditions. So then the log decrement is decreased. This is the destabilizing direction. And then the sum of the shunt gas injection is added and then tested the same high pressure condition. This is the log decrement is much improved by the shunt hole injection. This is the comparison data of the with shunt hole, without shunt hole. This figure shows the simplified rotor stability. This is the rotor and at operating mode is like this, and stabilizing by the bearing damping coefficient and also the deflection at the bearings is this. And when the labyrinth with cross couple coefficient and this uh, um, deflection at the labyrinth. So this is the energy of the damping effect, and this is the energy of unstabilizing effect. So if this value is higher than this value, system is stabilized. But on the contrary, this value is larger, the system is unstable. This is the speed increasing. Normally, the damping effect is decreasing due to this damping factor is smaller, decreasing while increasing the speed. But on the contrary, this cross-couple effect and also this deflection is also increased while increasing the speed. This is the threshold and stable and unstable at speed. So if this value is higher than the stabilizing force, system is unstable. Part 6. Fluid dynamic performance test. Most popular fluid dynamic testing is the ASME PTC-10 performance test. This test is intended to determine the following key parameters of the compressor at site operating conditions. 1. Quantity of gas delivered. 2. Pressurized produced. 3. Head produced. 4. Shaft power required. 5. Efficiency. 6. Surge point condition. 7. Choke point conditions. 8. Other flows instability like a rotation. To conduct the test, two types of tests are specified. Type 1 test conduct with the specified gas at or very near the specified operating conditions. Deviation in the specified gas and operating conditions are subject to the limitation imposed by Table 3.1 and not to exceed the limit of the Table 3.2 of this code. These tables are shown on the next page. Type 2 test limits are Table 3.2 only. The specified gas or substitute gas may be used. The test speed might be different from the specified combustion speed due to the test gas selected. ASME PTC specify the type of testing given in this table using the actual specified gas and inlet conditions. For the thermodynamic point of view, deviation from the specified condition given in this table shall be met.